So I've structured my talk today in part as more of an educational background into tribology in order to get a good understanding and hopefully to impress upon you the benefits of nanotechnology, specifically nano additives and lubricants. So to start off, it's a focus on what I call the real cost of lubrication. As I say here, real cost has little to do with the actual cost of the lubricant, and instead is associated with the cost associated with the failure to have the right lubricant in the right place at the right time. In many ways, it's analogous to the iceberg in the water situation, where typically most people consider cost of lubricant as literally just what's above the water, whereas as we've seen from Chris's talk even, the costs associated with downtime, maintenance, safety, and in this case from the wrong lubricant can be quite significant. So tribology is concerned specifically with obviously contacting surfaces, metal surfaces. They can be same materials, different materials, but it's a direct focus on the study of friction, wear, and lubrication. So a little market research has been done. Originally a report was published in the mid-60s called the Jost Report of the United Kingdom that estimated about 2 to 3% of gross domestic product is lost due to lubrication inefficiencies. Numerous studies have been published since that time. Canada has its own study commissioned by the National Research Council in the mid-80s. And more recent research basically shows, just in terms of actual efficiencies, that we have approximately about 4% or 0.4% rather of GDP. In terms of actual numbers for Alberta, that works around to about $1 billion just in terms of loss efficiency. That doesn't include actual downtime, maintenance, repair, equipment replacement. So as I say here, to extract the savings, it's important to have a good understanding of tribology. And a few specific examples. Marin focuses on extreme pressure and anti-wear additives, particularly in heavy equipment. We've done quite a bit of work with some aviation applications, helicopters, looking at the rotor shaft assembly of the main rotor hub and the tail. Again, in the mining industry, both for engine additives, fuel-based additives, and a little closer to home, this is an area that we're starting to investigate a bit more, and that's wind turbine lubrication. And I have an example here. At the end of the day, the main challenge of a lubricant is to fight friction and wear. I mean, that's the ultimate goal. And the example down here, this is a Vestas 3 megawatt generator out of Holland that ended up catching fire and burning down to the ground. And the root failure analysis revealed that it was actually the lubricant in the gearbox that failed. They were testing a new lubricant that wasn't adequately protecting the gearbox. Temperatures got high and the actual oil started on fire, consequently burning down a multi-million-dollar wind turbine. So when it comes to formulate an actual lubricant, at the end of the day, the base oil is your starting foundation, and the additives are the house that goes on that foundation. As I say, you can have a base oil that's identical in an engine as a hydraulic oil, but it's the additives that will ultimately differentiate what that is. And as I just mentioned, our focus and my specific focus is on the anti-wear and extreme pressure additives. So tribal systems are defined as just two surfaces, and again, they can be same material, different materials, separated by an interface. In most cases, we're obviously talking about an oil-based interface or a lubricant, and then environmental effects on that tribal system. When it comes to friction, in the world of tribology, it all breaks down to asperity contact. And those are simply just points in contacting materials that are coming into contact as those two surfaces oppose one another. That leads to friction and a whole variety of wear mechanisms. Specifically, all metal surfaces, irrespective of how finely polished they are do contain asperities. This is just an example of a roller bearing 316 stainless steel and AFM image. In this image, basically, the dark areas correspond to valleys, and the light areas actually correspond to peaks, or in this case, asperities. So as you can imagine, when you have two of these surfaces coming into contact, if you can't keep them separated by a lubricant, the asperities will come into contact, and as a result, you'll lead to increased friction and increased wear. So if I had to sum up the entire field of tribology in one slide, this would be it. essentially, there's really three realms that we're dealing with. Full film lubrication, that depends exclusively on the viscosity of the lubricant to keep contacting surfaces separated. Mixed film lubrication, in which case the viscosity is able to keep the surfaces mostly separated, but there is some asperity contact. And then finally, my area of focus is the boundary lubrication realm, and that's where the viscosity cannot keep the surfaces separated at all, and you have direct metal-to-metal contact. As a result, you need specific or unique chemistries to actually protect the surface that will instead wear versus the surface you're trying to protect. So why nanoparticles? There's lots of reasons. I'm not going to go through all of them just to keep the time short, but the main ones I want to focus on are on the right side here. And one of the most important ones that nanoparticles have over conventional chemistries used as extreme pressure and anywhere additives is a temperature benefit to them. And that is, nanoparticles do not have an induction period. That essentially, there's always a requirement for most chemistries that enough energy has to be put in before they activate and react. In most cases with the nanoparticles, simply enough pressure into the system will cause the necessary reactions or protection of the surface. Focusing on the different types of chemistries that are available, the main two classes involve the organic nanoparticles and inorganic. My focus today is just going to be on the inorganic here, so I'm just going to ignore the carbon side for now. But specifically, two of the most common used in the lubrication industry are molybdenum disulfide and tungsten disulfide. Part of the rationale is the structure that these materials form. As we can see here, these blue-colored atoms correspond to the metal, so either molybdenum or tungsten, and on either side of them correspond to sulfur atoms. And these materials actually form layers or sheets that are simply held together by intermolecular interactions. And when you apply a shear stress to these layers, they easily separate. So the benefit is they offer an incredibly low coefficient of friction. But two, they can also be converted or combined or manufactured into nanoparticles that have related and also additional wear benefits associated with them. The advantages of materials like molybdenum tungsten disulfide is they can be used directly without much further processing in greases and pastes. And as a result, there's a lot of commercial products available today that do use them because they provide a significant benefit and reduction in friction due to rolling. The main problem, though, is that nanoparticles, and this is a generalized statement, inherently are not soluble in oil unless specifically manufactured to do so. And that's pretty much any oil that you can throw at them, mineral, synthetic, renewable sources such as vegetable-based oils. In essence, what happens is when you put the nanoparticles in oil, they form suspensions. The classic example I have here on a macro scale would be like putting flour into a glass of water. That over time, you can initially get a nice dispersion, but you have aggregation and flocculation, and as a result, it separates out. You can imagine in a lubricant, you do not want your anti-wear and extreme pressure additives separating out into the bottom of the lubricant. So the answer to that is to develop chemistries and methods that actually produce a colloidal mixture. And again, the real world example is milk, which is a colloidal mixture or emulsified colloid of butterfat molecules in water. So the two ways of manufacturing nanoparticle additives or incorporating them into lubricants is ultrasonic dispersion. This is sort of the low-cost method. And the more elegant but more expensive method is surface modification of the actual nanoparticle. There's quite a variety of different technologies, of different nanoparticles. I'm not going to go into any great detail. The big focus to date has been on the molybdenum tungsten disulfide. The two largest manufacturers right now is a product called Nanoglide out of Arkansas and another one called AP Nano based out of Israel. Our focus has been on borate-based chemistries for use as anti-wear additives. So what are the advantages? As we've kind of already alluded to, reduced downtime of maintenance, so you have fewer equipment problems. You can extend your relubrication intervals and as a result use less lubricant annually. And kind of related to extended relubrication intervals is improved efficiency. And that manifests itself as lower operational temperatures as well as enhanced fuel economy. But one of the biggest benefits that can be achieved with some of the nanoparticles is an environmental approach. What I mean by that is it's possible to achieve the same level of performance as other or current extreme pressure and anywhere additives that are using zinc, sulfur, and phosphorus, but do so without them with the nanoparticles. The last two slides I have here are just what I call the commercialization challenges. Specifically from a synthetic perspective, it really breaks down to currently cost, and that's cost of raw materials. The first example here is the differentiation between tungsten, molybdenum, and zinc. Zinc is the most widely used anywhere additive in engine oil today, diesel, passenger vehicle oil. One of the reasons for that is the current street price per pound of molybdenum tungsten is $19 and $17 a pound. Zinc has a current street value of just $1.05 per pound. So in terms of even just raw material processing into a useful technology, raw material costs are one of the prohibitive factors. And coming from that is that current extreme pressure and anywhere additives do cost less than nano additives, but they're often not as effective, and in many instances they are harmful to the environment, and that's why new regulations are trying to restrict their use. In order to kind of push such technologies, it really comes down to the acceptance and adoption. There's numerous standards, obviously, in a whole variety of different types of oils, engine oils, hydraulic oils. Most of these, fortunately, are fairly easy to meet, even changing to a new technology or a new nanoparticle type technology. And it really breaks down into getting large players, early adopters, to test in an actual field test. So for us, currently where we stand right now with our technology that we've developed to date, it really breaks down to, as we say, timing, consumers, and distribution. Timing for us, this product actually is complementary to our other technologies available. The main thing is identifying those in the market who require an increased performance at the same time in environmentally sensitive areas. And for that, our users typically fall into currently mining, utilities, and forestry, or those who are working in environmentally sensitive areas who are restricted in what types of products they can use. And then two, since that we're a smaller company, our main arm of distribution is leveraging our current business relationships that we have, developing new ones through meetings like this, and as well working through our existing distribution network of owner-operators and service contractors. So that brings me to the end of my talk today. I'd like to thank Ash for the opportunity to present, and you for your kind attention.